I'm the same distance from the sheet on both sides. So what I'm making the claim is that the electric flux on this surface and the electric flux on that surface are the same. My area vector points that's my electric field, and that's my area vector. Over here, that's my electric field, that's my area vector. It's just the electric field times the area of the end cap. So it's going to be 2 times my electric field times my area, which equals my enclosed charge, sigma times A, over epsilon sigma. My area vector cancels out. And what I'm left with is the magnitude of my electric field is sigma over 2 epsilon sum naught, which is what we had before. So we've just used Gauss's law. There was a video where I go through the formal derivation of Gauss's law when I did it 2 weeks ago, a week ago. I did a specific case, and then I just said, hey, you can generalize it. But the more formal derivation, I did a video for. I don't think anything's gaining from it right now. Or might do it in class.
So can you say why the side is 0? Or you cross it out and it's 0?
All right, so if I look at a side view of this, that's my surface of charge. At any point here, I'm going to have an electric field. I'll have a point here creating an electric field in that direction, a point here creating an electric field in that direction. So what I'm getting to is that for any point creating an electric field at this point, there's going to be another one that's going to cancel out any of the way I've drawn it, any vertical components. The only thing that's going to be left from any of these electric fields are in that direction. So first you have to accept that the electric field has to be, in essence, perpendicular to the surface of charge.
Okay.
Area vector is perpendicular to the surface of the object, of the cylinder. So if I'm on the side here, or like this, my area vector on the side is pointing this way or that way, perpendicular to it no matter where I am.
From the side?
Yeah, it's perpendicular to the side, which is going to be perpendicular to my electric field. My electric field's running this way, my area vector on the side is pointing perpendicular to that. When you do a dot products multiply parallel parts. If 2 objects are perpendicular to each other, the dot product is 0. Sorry, if the 2 vectors are perpendicular, the dot product is 0.
Okay.
That's how we get 0.
And the other one, the left and the right, cancel out because it's not from a side view?
Oh, what, this?
Yeah.
When we did the line? When we did the line, they didn't cancel each other out. They were
They're 0.
0 because my electric field is pointing away from the line, my area vector is parallel to the line. So anywhere on the end cap, the electric field is perpendicular to my area vector.
Okay.
Is that sufficient? Okay. Other questions? All right, so those are 2 derivations we've done already. We did more complicated versions of the derivation. Now it's actually applied to a slightly different technique where we're not deriving formulas we've already derived. If I take, we'll just start out with a sphere. I take a sphere, solid. And I throw a bunch of excess charges on it, solid conducting sphere. and I throw a bunch of extra charges on it, what will the charges do?
Spread out.
Okay. Where?
It's conducting, wouldn't it go through the sphere?
Okay, but where will they settle? You say
Inside the sphere?
inside the sphere?
Say your question again?
If I have a solid conducting sphere and I throw charges onto it, where will the charges go?
When you're throwing electrons onto it?
Yeah, that works.
They stick on it?
I mean, they would just.
It's conducting, so they will start to move.
they'll
All right. So you're saying that they'll spread throughout? I thought that's what you said earlier.
You can charge the outside.
And you're saying just the outside would be charged?
Yeah, too.
Remember, the electrons hate each other. They need to spread out as far from each other as possible. If I have any in the middle, then I'm gonna have some that are a lot closer to each other. They're still gonna push against each other, and they will spread out to the surface. So what are the rules for in electrostatic equilibrium? If a conductor is in electrostatic equilibrium, excess charges will settle on the surface. So if I imagine, I'm just looking at a cross-section of the sphere, if I've got the solid conducting sphere, and this has, we'll just say, -4 coulombs of charge, then -4 coulombs will spread throughout the outside here. I'm not saying there's no electrons in the middle, I mean, there's still atoms inside here. And not all electrons can easily travel. They're not part of the electron sea. So now I'm gonna take that and I'm gonna create a cavity. So I basically got a hole in the middle of my sphere. What does that change to my excess charge?
It could now spread out through the surface of the hole.
Say it again.
It'd be able to now spread throughout the surface of the hole for now.
Is there anything drawing them to the middle? She says no.
Not particular, but
Yeah. No, it doesn't change anything. Putting a hole there doesn't change anything. Yeah. If there's nothing in there, there's nothing that's gonna draw them to it. Now I'm gonna take that hole and now I'm gonna stick something in it. So I have -4 coulombs, so this around the edge here is still -4 coulombs. Now I'm gonna take that hole there, and what I'm gonna throw into here is a 3 coulomb charge in the middle of that cavity. So here, this is the flesh of the pumpkin, and that's the hole in the middle. Yeah, pumpkins have holes. Okay. So now I have something that's gonna draw electrons in towards the middle. Question is, do they all get pulled in? They still hate each other, they still wanna get away from each other. How much is going to then be drawn towards it?
What did you stick in there?
3 coulomb charge.
-3 coulombs.
It will indeed be -3 coulombs here at the surface, and then what, here will be -1 coulomb, because I still have -4 coulombs here. So when I say it resides on the surface, it can be inner surface as well, as long as there's something to attract it. Now let's actually show that why that has to be, assuming Gauss's law is true. So what I'm gonna do is I'm gonna create a Gaussian surface here, a Gaussian sphere, where the radius is in the fleshy part of my annular sphere, my thick walled sphere. We showed earlier when we were dealing with forces that if I have a sphere with spherically symmetric charges that on the outside, then the force on the particle inside is zero. If I'm outside, I got spherically symmetric distribution of charge, and I'm outside, I can treat that as a point charge. But if I'm inside, the force on it is zero. So, excess charge from site on the surface. This is something that we did in day 1 or 2. The electric field inside the material is zero. Now what we showed was the force was zero, but if the force is zero on a charge, then the electric field is zero. So I'm inside, if this is an electrostatic equilibrium, I'm inside this, then I know the electric field going through my Gaussian surface is zero. Applying Gauss's law, the electric field through some closed surface is equal to the enclosed charge, the enclosed charge over epsilon sub naught. I know this is zero because my electric field inside is zero. Therefore, my total charge inside my Gaussian surface has to be zero. So if I put a positive 3 Coulomb charge here in the middle of the cavity, there has to be negative 3 coulombs right on the surface there, because the total charge has to be zero. Let's make it look more complicated. Or questions before I make it look more complicated. Hopefully not questions on the thing I just erased.
The circle above the E that equals zero vector, that's a zero, right?
That's a zero. Yes, that's a zero. That is, and that is, that's a capital 5.
There's so many circles.
And I insist, when I taught elementary school, I did write Euclid. I guess I should ask my daughter. She was in there. All right, let's make it a little more complicated.
So nice to see.
What are we looking at?
So I've got a sphere with a cavity in it. Inside another, I guess it's a shell at this point, a shell with, so with the dashed lines indicate there's some metallic substance, some metal material, solid, and the blanks here represent empty space. So basically I took that and then took a bigger one and stuck that inside it,
Okay.
the turducken of physics. So I'll have an excess of 10 coulombs on this ring, and I'll have an excess of negative 3 coulombs on that ring, and here I'm going to put a charge in the middle of, I'm going to say 5 coulombs. And what I want to know is what is the distribution of charge on each of the surfaces? Or, sorry, not distribution, what is the charge on each of the surfaces? It will be distributed evenly.
Would it depend on how far away it is from each surface?
Did how any sizes fall into? Well, no, not in terms, if I wanted to find the electric field, then yeah, I need to get a little bit more information.
It'll be 6.
Pardon? 6
coulombs
Where?
on each one.
No, not 6 on each one. Let's see if this will work. All right, so I've got 1, 2, 3, I have 4 surfaces. So I need to figure out what's going to be on this surface, the charge on that surface, the charge on that surface, that surface, and that surface. First off, what's gonna be the charge on this very inner surface?
Negative 5 coulombs?
Yep. For the exact same reason as over here, we created a Gaussian surface. The electric field inside the fleshy part is 0, so the flux is 0, so the total charge inside that must be 0. So this is negative 5 coulombs. What is going to be here?
Negative 3 coulomb. Negative.
If I put negative 3 coulombs here, we have negative 5 coulombs here on this inner part. If we put negative 3 there, that means we have a total of negative 8 coulombs.
Positive 3.
If I put positive 3 and with a negative 5, we now have negative 2 coulombs.
Give me 7.
If I put 7 here, with that negative 5, I now have 2 coulombs.
This is 5 coulombs.
Sorry?
It's just 5 coulomb.
I have this is the total excess charge in that this inner shell. Ferris?
0 to 0.
Oh, no, I thought you said something else. All right, let's just drop back for a second. It's not you're making it way complicated here. I know the total charge on this is negative 3 coulombs because I said so. That negative 3 coulombs has to be the charge on the inner surface plus the charge on the outer surface.
So it's just 2 coulomb.
Negative 3 is equal to negative 5 plus that charge on the outer surface.
It's 2 coulombs.
2 coulombs. Okay. It was interesting to look into where your minds are, but I'm not quite sure how you're coming up with a lot of those numbers. I mean,
So then the next inner surface is negative 2? Wait.
Minus 2.
so here, on this surface here, how do you get negative 2?
I don't know.
Is it the same process? Is it what you just did?
Yeah, same process. So what is the total? I know that here, the electric flux is 0, because the electric field is 0. Therefore, whatever charge is inside this pink Gaussian surface must be 0. Well, I got 5 and negative 3. Yeah, so that would be 2 there, so there would have to be negative 2 here.
Oh.
Sorry, I thought you were answering a different question.
Okay, well that was my first guess.
Yeah,
0,
your
1.
gut feeling was right then.
Yeah.
And so therefore, on the outer surface here,
It's 12 coulomb.
all right, questions before I add stuff to it? Let's see. Different color.
Why is the last one 12?
Because I know on this outer ring, my total charge on it is 10 coulombs. And negative 2 are on the inner surface, so there has to be 12, because when those add together, I get 10.
And then for the very inner ring, it's negative 5 because that one charge is 5, right?
Correct.
Okay.
And the same reasoning that if I did a Gaussian surface here, the electric field I know is 0 because I'm inside the metal, the conducting bit. And since the electric field is 0, the electric flux is 0. From Gauss's law, that means the total enclosed charge is 0. So if that's 5, that's gotta be negative 5 to balance out.
Why is the middle one negative 2 coulombs?
Negative 2.
Yeah.
Again, this pink Gaussian surface, I know my electric field inside a conductor in electrostatic equilibrium, the electric field is 0. If the electric field is 0, the electric flux is 0. The electric flux has to equal the total enclosed charge divided by epsilon naught. Well, if my flux is 0, then the total charge has to be 0. Well, I've got 5, negative 5, and negative 3. Oh, no. I have 5, negative 5, and 2, which is 2. So this would have to be negative 2, so the total charge is 0. that 3 is not on the surface, that's the sum of those two.
So can we ignore the 3 when we're looking for the other one? That -2?
That -2,
Yeah, when we're looking for that, we can just look at the,
I can do it one of two ways. One, I know I have -5 coulombs, I have +5 in the middle, -5 here, and 2 here. So I can just add up what I have on the surfaces. Or I could just, that's 5, and this inner ring I know has a total of -3, add those up, I still get 2 total.
okay.
Right, let's throw some distances into it. Let's make this, let's see. So that will make 2 centimeters. 5 centimeters. 8 centimeters. 12 centimeters. I want to know the electric field. At 1 centimeter, the electric field at 4 centimeters, the electric field at 7 centimeters, the electric field at 10 centimeters, the electric field at 20 centimeters. All right, so at 1 centimeter, I know I've got this distribution of charge. Let's see if I can draw it slightly more neatly.
0.
So I have 5 coulombs there, I'll have -5 coulombs there. Then I've got